Let's see, as we're getting started here, just remind everybody that after class, or 2 nights ago, whenever it was, I posted up the solutions to the exam. I posted up the histogram tagged at the back of that, and I also have a histogram tagged at the back of that that has the quiz average, just the raw first 5 quizzes is a histogram averaged up, so you can take a look at that. And I also have the senior design feedback sheets, but I forgot to post that up because I got into this discussion and didn't get that done. But if you want to follow me back to my office, that only applies to 3 folks in here for your teams. 4. I can give you the stuff after class if you want to come and get it from me. So let's go back and look at the mixing stuff. So to me, the best example is just, this is the spectral layout, and the math is in between the block diagram and the pictures. So frequency translating and mixing, if this is a radio receiver, it's just saying that you want to move something to a common location that's useful for all the purposes of demodulating and recovering that signal. So this first example was AM radio, which is at a relatively low frequency, 540 to 1600 kilohertz. But the common frequency is, in this case, is 455 kilohertz. So that's where this channel tunes at, is 455 kilohertz. And then you have anything coming in out here from 540 up to 1600, and everything is spaced on 10 kilohertz spacings. So if you were sitting and thinking of, I'll just draw this as a positive sided spectrum. If you look at this as saying you've got 540 to 1600, all those little humps represent possible channels that are out there, spaced every 10 kilohertz. And we're saying in our receiver, we're going to put our common IF frequency right down here at 455. So that's a bandpass filter that's sitting right in there. That happens to be that bandpass filter right there. So now we'd like to bring everything through that common frequency by making it pass through that common frequency using the local oscillator that comes into the mixer, the multiplier. And we know that a multiplying of a cosine times a cosine, and we think of a carrier wave as being cosine with some message on it. It's either AM modulated, double sideband, or, as we're going to start on today, the angle modulated. So it's in the argument of the cosine, but it still doesn't matter. The trig identity still applies. The trig identity of cosine times cosine is going to produce a sum and a difference frequency. So the mixer output will be a sum and a difference. We get our options actually with a frequency translator, and I didn't really dwell on that before, but the output we can choose is either the sum or the difference. It doesn't have to be the difference. It just is one of the two that we would like to have. So in this case, though, it is the difference that we're looking for. The difference is at 455. And I guess if you look at the simple math involved, I can't do anything with 540 by adding a frequency onto 540 to get to a lower frequency. Do you agree with that? So I do have to use a difference. So you might be thinking, why would you ever want to use the sum? That can be done. And in certain applications, you actually choose to move the frequency up higher rather than down lower. That could happen in a block converter operation, where you might want to move a band of frequencies just up to a higher frequency.
So it'll typically move them lower?
typically move it lower, most receivers, because
The difference is the one difference.
yeah, the difference is normally what you use. But
What about when you're needing to transmit it through like a different kind of medium, or like you could like transmit to a satellite station and then from there transmit to a satellite or something like that?
yeah, and that'd probably be a good application. What Rob is saying, that you would start at a lower frequency and then you want to move it up to get it out to the transmitter and the antenna. You have a microwave amplifier, power amplifier, or HPA as they call it, high power amplifier, and it's starting at a lower intermediate frequency, which I guess would be typical of a box at RT Logic or Emergent or somebody like that. You start at a 70 megahertz intermediate frequency and you're going to move it up to a higher one. The customer is, let's say, and the customer provides you with a 70 megahertz IF already. That's the way a lot of satellite systems work. So, but we're talking receiver, so I guess in the receiver maybe it's definitely safe to say you move it down. But there can be different reasons you might need to move it up. So the difference is what we're after. So we set a local oscillator signal at either 455 kilohertz above or 455 kilohertz below, and that's why the plus minus sign is in there. Because you can either set it above or below. You're just looking to make sure the difference is at the IF frequency. Does that make sense?
So would you see image frequencies if you use the low side, the FC minus sign?
You can see
Yeah, you've seen both ways.
image frequencies.
It's always, as the formula states in the book and in the notes, it's always at twice the IF frequency of the signal that you're converting. To me, it's easiest to see from a picture, though. I mean, that's where I think it's easiest. If I was going to go with the high side tuning, which is what I did in the example here, I've got the picture where my desired is at 560, so I set my local oscillator at 1015, and that is exactly 455 above 560. So it produces the difference you see right there at 455, 1015 minus 560. And the image in that case is another FIF above my local oscillator, so it's at 1470. And you look at, from this diagram, you look at the relationship. The key is that there the difference is 455, so that makes 560 convert to 455 with the 1015 local oscillator. And also the difference here is the same way. It's 455 difference. So 1470 is converted to 455 with 1015.
But there are two carrier frequencies that you could demodulate at the 560 kilohertz, get it to 455 kilohertz, right?
Yeah,
It would be the sum, which is what's up there, the 1015.
Yeah.
The difference. And if it was the difference, then wouldn't the image would have to be on the low side, but you run out of spectrum because then it becomes negative. I guess that was my
But okay, that's your question. Okay. It doesn't really become negative because if it's a real signal, it's symmetrical. So the spectrum will have its mirror, and that's what you'll be working off of then.
So if something goes negative, then it's just you.
Now let's,
Okay.
if that's bothering you, that might be bothering somebody else. So let's take a look at that real quick now. So we were trying to convert to 455. We were at 540, right? 560, okay. And you were saying, suppose I choose the local oscillator below. So I have to get a local oscillator signal that's sitting right in here. No, sitting way below that, excuse me.
Maybe down at 105.
So 105 produces a difference between here and here, which is at 455. And then you're wondering what makes 105 vulnerable to 455. It's actually going to be a signal that would add to 105 to produce 455. So that would be, let's see, got to do my math, 450, right? No, 350.
Okay. For which one?
350 plus a local oscillator at 105 would equal 455.
Where'd you get the 350 from?
Because I'm looking at my picture as opposed to working the equations, which to me makes more sense. But the other way of looking at it would be that according to the rules, you'd have to go 455 below this 105, and that's going to put you at minus 350. But what I'm saying is, because it's a real signal, we know that, there's its negative spectrum. And likewise, if there was a signal sitting in here at minus 350, it would also have a copy sitting there.
Okay.
And the sinusoid, the spectrum of the local oscillator itself has got a spike at the positive and negative frequencies. Right? So does that answer the question? I'm in favor of drawing pictures, though, because the pictures just help bring some clarity, because negative frequencies seem strange, because you never think of a radio with a negative frequency part on the tuning dial. But that's my generation. Tuning dials, the modern era is just digital tuning, and you don't think about that. But okay, question?
So this is one of those instances where it's good to draw the double-sided spectrum, because otherwise you wouldn't think that there could be a problem.
Right. But I'll just tell you, in most instances, you don't work that low in frequency where it goes negative. There are occasions, especially with digital signal processing, where you can work with complex sinusoids, and then you can be unique. You don't necessarily have a spectrum that has a mirror image. Only real signals have a mirror image on both sides. If you have a complex signal, it's unique. It doesn't have to have a mirror image sitting over here. We're trying not to dwell on that in this class to avoid confusion and to stay with reality. When I say reality, I mean the fact that in analog signals, we have one line carrying our signal. If you had to have a complex signal, you'd have to have two physical wires to carry that complex signal. But in digital signal processing, not a problem. You just have to have a data structure that holds the real part and the imaginary part. And it's done all the time. And someday, I suppose that's the way we're going to have to teach it, because everything will be entirely in software or in discrete time domain, and it only switches out to the real signal domain when it goes out the transmitter or right after it comes in through the receiver, the RF front end.
So that 350 is where you want to put which signal?
The 350 is where the image would be. This is the image. If you did low side tuning, in that case, that's where the image would be.
And the red's our signal.
Yeah. Sometimes called a SOI, SOI stands for signal of interest, and SNOI stands for signal not of interest. So people say, when I started getting into this, I'd hear people talk about SOIs and SNOIs. They, engineers also have to pronounce their acronyms, so I think that's more of a military context, the signal not of interest and the signal of interest. Okay, let's go back over here and see if we can roll forward. Well, some of you are going to be in the infrastructure and you're going to be doing this stuff, so. Okay, so that allows you to see the image, and then the other thing you get to see once you identify the image, now you know what the design of the receiver can do to protect itself. The picture here, if I can get it to scroll back, it's now going to mess up on me. Yeah, it's not going. Yeah, it did. This tunable filter out here is sometimes called an image rejection filter, because that's what its purpose is to reject the image. It actually can serve more than just rejecting the image, but it has a primary role of rejecting the image, because if we look down below here, let me just do it this way. If we look down below here, you can see that by putting the filter that I've got sketched out over here over the desired signal or signal of interest, as long as it can roll off significantly, it will keep the image from getting in the front end of the receiver. But the problem with that filter is it needs to be tunable if it's a tunable receiver, so that's an added complication. One of Dr. Kalker's things that he likes investigating or building with his thin film ferroelectric materials is capacitors that can be tuned with a voltage that can form tunable bandpass filters. There's also another device called the varactor diode, or variable capacitance diode. That's what I'm familiar with using, but he uses the thin film ferroelectric capacitors. But not all applications require tunability, so that filter might just be fixed, and it might only need to be made wide enough to get all the signals of interest tuned in, and you don't have to keep changing it. So that protects you from the image, but you realize your real filter comes along and it's going to have some roll-off on it in dB. So the question is how many dB down is that filter going to be over here? Is it going to be 30 dB, 20, 40, 60? I mean, how much can you afford and how much do you need to afford? That's kind of up to the requirements of the receiver. Question?
So if this is a radio station, you would still need, you wouldn't, obviously can't listen to it at the intermediate frequency still.
Right.
You still need to modulate it, but in your block diagram, you
Mm-hmm.
have an envelope detector. Does the envelope detector filter and demodulate, or is there something
That envelope detector is just what we talked about. It has the RC in there after the envelope detector. So
rectifies?
then removes the carrier. In this case, the carrier that it sees is at 455 kilohertz, but it still serves the same purpose as the real carrier, because it is a carrier, it's just at a lower frequency. And the other big advantage is the amplifier of the IF filter can be made to have a really high gain, because the AM signals that impinge upon us and the receiver's antenna are very, very tiny. So you need a lot of gain, on the order of maybe 60 dB of gain, to bring the signal up from the microvolts per meter type range to volts, right? Or fractions of a volt to get the envelope detector to work. So it's a lot easier to build a high gain amplifier that's in a narrow band of frequencies than it is to put the high gain out there at the front of the receiver. Because if you put the high gain out there at the front of the receiver, the really high gain, it will get swamped out by any little spurious signal that happens to come floating in, and then it might start overloading and creating a bunch of distortion products that are not good, since there's no such thing as an ideal amplifier. Is that good enough?
Yeah.
The dual conversion just does 2 of them for reasons that I talked about in there. Okay, now into angle modulation. So the focus for these next many pages on through phase lock loops is message is somehow or another related to the angle of the cosine carrier. So back in 2610 is where you first get introduced to this concept in at least one of the labs. I mean, one of the labs that I usually do when I teach that class. But what we can do now that we've been dealing with cosine carriers a lot is we can say, what's the argument of the cosine? That is the instantaneous phase of the signal, because that is what the argument of a cosine is. It's something in radians, right? That's the argument that a trig function takes. So the instantaneous phase is the entire argument. Carrier, which is a linear phase, omega ct is just a phase that's ramping, plus a deviation, phi of t. So the phase deviation is the part that is separate from the linear term due to the carrier frequency itself. The derivative of the instantaneous, well, the instantaneous frequency is the derivative of the instantaneous phase. So that's composed of the carrier frequency itself and then the frequency deviation. And here the frequency deviation is in radians per second. But we'll be dividing it by 2 pi ultimately to get it in hertz, because that's typically the way most communications engineers think about the frequency deviation, just dividing it by 2 pi. So if you do phase modulation, we're just making the message proportional to the phase deviation, and the deviation constant is kp, and kp just has to have units of radians per whatever the units of m of t are. Oftentimes it'll be voltage in a modulator, it might be current, or in digital signal processing it's just dimensionless because it's just something on the computer. But it converts the message into a phase deviation as a function of time. Frequency modulation is where the message is made proportional to the instantaneous, or the frequency deviation. So d phi dt is kf times m of t, where the deviation constant would have units of radians per second per unit of m of t. Or turning that around, integrating both sides, you've got the phase deviation is equal to kf, the deviation constant, times the integral of the message, plus phi 0, which is just the constant that you get when you integrate something. You have a starting time, and then the phase of the carrier is phi naught at that start time. It's common, very common in our book here to use, instead of kf, to use fd as the deviation constant in hertz per unit of m of t, and then just multiply it by 2 pi. And this is what I was talking to you about last time when I was saying this is describing actually a VCO.
So frequency and phase modulation are both stored the message inside the carrier signal's phase?
They put it inside the argument of the cosine, yes. And what's cool about that is the envelope of the signal is constant. It does not fluctuate. It's just what's inside that deviates back and forth, so it has what's called a constant envelope. Now that gives it some very nice properties. Constant envelope signals can get amplified even by nonlinear devices, and it doesn't alter the modulation. It does produce harmonics of the carrier and so on that you might have to take out with a filter, but it has some nice properties for processing these types of signals, say in satellite communications, where you want to run the amplifier close to being in distortion, but you don't, and you want to have a very efficient amplifier, kind of like the class D, but not to that same extreme. It's more of a class C kind of an amplifier. And people have known this for a long time, because sending signals down from satellites is not cheap, and you want to have, solar power to drive the power amplifier. You want it to be efficient a conversion as possible. What I was getting at with the VCO is generally a sinusoidal oscillator that will produce an output. I'll just call it x sub c of t, whose frequency can be made to deviate about some quiescent frequency by whatever you apply to the input to the VCO. So the output frequency is proportional to the input frequency, or the input signal, through a deviation constant fd, so many hertz per volt or megahertz per volt, And then if there's no input applied to the VCO, it sits at a quiescent frequency. And I was asking that question when you left class last time, do you still build oscillators, voltage-controlled oscillators in electronics? I think I gathered that the answer is no. Dr. Kelker has you build them. If you take his RF circuits class in the summer, I think you build a VCO. No? Not a VCO? Well, if you build an oscillator that has an LC tank circuit in it, you know, an inductor and capacitor, all you have to do to make it a VCO is slap a varactor diode or some diode that you can change the bias on to change the capacitance, and then the tank circuit's center frequency changes, and you just decouple that from the RF so you can feed a signal in, and then you got a voltage-controlled oscillator. So just to sort of illustrate the differences between phase and frequency, suppose we're going to put a step signal into a modulator, or M of t is U of t. For the case of phase modulation, I'll just suppose that the phase deviation constant is pi over 3 radians per volt. And for the case of the frequency modulator, I'll assume that FD is 3 hertz per volt. So if I was to go through this modeling, what would be, when I put my signal in and it steps by 1 volt, I'll instantaneously step the phase of the carrier by pi over 3 radians. And when I go the FM signal route, when I step the input to the modulator with a step of 1 volt, it'll hit this 3 hertz per volt, and it will produce a 3 hertz frequency step at the output. I mean, the frequency of the carrier will jump by 3 hertz. The phase that will incur will be a linear phase due to the integral of the step, going through this integration here. And if you're wondering why there's no limit here, it's sort of customary to say we're just integrating and we're taking out at time t, and by not putting the lower limit in, it's a crude notation to say I don't care about the initial condition. It's just started somewhere and we're not really concerned with it. Another way of thinking of it is we'll just assume that it's 0 unless you're told otherwise.
So for KP and FD, are those always going to be set?
Those are constants.
They
They don't
don't vary.
vary. You might change the setup in a modulator to change the deviation constant. That's one of the things I was looking at in some materials for the project I'm working on for the Air Force Satellite Control Network. It uses phase modulation with what's called subcarriers, and we'll get into subcarriers much later in this chapter, but the deviation constant can be changed for different modes of operation. There's many modes of operation in the requirements document. So these two plots show you what happens for phase modulation. You just see a sudden jump in the phase, so it instantaneously is jumping by pi over 3. Whereas in the case of FM, because you're running it, the signal message is going through an integrator, instead of getting an instantaneous phase jump, you get an instantaneous frequency jump. So now the oscillator goes from a lower frequency to a frequency that's 3 hertz above. Does that make sense?
The integrator is, in this case, it's allowing the phase to be linear, so it still looks like a sinusoid.
Yeah.
Okay.
And it's also continuous. That's another thing you might notice. An integrator ensures that it's continuous, because as you start integrating that step, it turns it into a ramp, right? So you don't see a sudden jump with the frequency modulation like you do with the phase modulation.
So is that signal then, is that X P M of T? Is that coming on the left?
Yeah, both of these are the carrier signal. So these are both XC of T.
Right, but are they? Oh, in front. Okay. See.
So Sean's question about where is the modulation, notice it's constant envelope. You don't see any fluctuations in the carrier itself. It's just hold steady and constant. And that's desirable. Actually, what you can also, if you were really thinking hard about the future, you'd say, oh, we've got modulation contained in the frequency or the phase. What happens if we start fluctuating the amplitude around? You can actually do a combination of the two if you want to.
So speaking of that, could you just put a bunch of carriers together, like you put a signal on a frequency modulation carrier, and then you take another carrier, you amplitude modulate the first carrier to that one? Does that preserve like the integrity of the signal when you demodulate the entire thing?
Well, what we're going to see later is called multiplexing, and it is possible to multiplex things together. It's actually possible to take one PM modulator and sum together a whole bunch of different signals, and you can actually put FM or PM on a subcarrier, and then put FM or PM on another subcarrier, and then put, say, AM on another one still, and still have another one at baseband. So you can put signals on carriers using any of the three modulations we've now talked about, the amplitude, double sideband or AM, FM or PM. As long as those carriers are distinct from each other, when they're summed together, then they can go into another stage of modulation, and then when you get to the other end and tear it apart, they'll be intact. And we'll be learning eventually that's how FM stereo works. If you've ever wondered about that, that's a 1948 vintage technology, but they figured that out a long time ago, that they could use what's called subcarrier modulation for FM stereo.
So does that preserve signal integrity better than just signal modulation?
Not really. But it gives options. I mean, the subcarrier idea gives the option that the one signal contains everything, and when you demodulate it, you can choose to ignore certain things. Like in FM stereo, if you don't want to receive the signal as stereo, you can just focus on the monaural part, which has the left and right channels added together, and you ignore the left minus right, which is sent on a subcarrier. So you can play games like that, and that is backwards compatibility. That's another thing that every engineer faces in your career. You've got legacy systems, and if a new technology comes out and standards are already in place, do you want to go buy new hardware just because, like buying a new iPhone, let's say? Why do we have to buy a new iPhone? I mean, that's or buy new of any type of phone. What's that? The economy, you mean? Or something else? Yeah. You don't really have to, though, right? If you wanted to be using, if you didn't want to be using LTE and wanted to use the existing infrastructure, you wouldn't have to buy the new hardware. Or you don't have to buy the latest Wi-Fi router if you're happy with the original Wi-Fi standard and don't want to use Type N or whatever else is new. So backwards compatibility is something that every one of us deals with all the time. When we do designs, we have to figure out ways to keep the old standards supported so people can keep listening. Even grandma and grandpa that want to listen to the AM radio and listen to music on that, they can find a station and use an AM radio that they've had for 50 years or more. They don't have to buy anything new.
So are these two modulation techniques directly related, or they're just two ways to do phase modulation? Like, could you get one from the other, or you
mean the FM or PM?
Yeah.
They are two different things in the sense that one, the message goes straight on through phase modulation, and the other one, it goes on by getting integrated first.
So don't think of them as like, we're just tracking them together in the notes, but not directly related to each other.
They are directly related through the integral or the derivative,
okay,
as far as that's concerned. But they have different behaviors, because you can't demodulate one without taking into account that one went through the integral and the other one didn't. So you have to design accordingly, especially if it's digital information. If it's analog information, they get used for digital too. They get used for digital as well. Remember when I was talking about listening to a fax machine? That would be this waveform over here. Frequency shift keying, you could have the carrier shift high and low with ones and zeros, and that's one of the original digital types of modulation. It used FSK as frequency shift keying. Gaussian FSK is what Bluetooth uses. It's not that far away from frequency shift keying. It's just got a pulse shape modification, and so on from there. Okay, there's a variant called narrowband angle modulation, which sort of backs up and starts all over again. And it says, let's write out the original angle modulated carrier as the real part of e to the j omega c times e to the j phi of t. This is equal to what we started with, right? This would be AC cosine of the same thing we started with. But by looking at it that way, you can then look at a Taylor series expansion or power series expansion of the e to the j phi of t inside that real operator and say that the power series for that exponential looks like this. And the narrowband approximation just says if phi is made small compared to 1, or have its magnitude small compared to 1, then you learn when you study power series that you can approximate it using just, say, the first term. The first term would be that. That's not too exciting, though. How about going one beyond that, include the first two terms, and then assume that phi is small so that we square it, and it gets so small that it's insignificant compared to the phi. And I'm thinking of, if phi is on the order of 0.1, then phi squared is on the order of 0.01, an order of magnitude below. So you keep the first two terms in the expansion. So this involves two terms, the constant plus phi, or the j phi. And because of that j, that comes out as a sign when you take the real part. So this looks almost like amplitude modulation. Amplitude modulation, you had a pure carrier and then you had the message going up. The only difference here is that now you've got things in quadrature, sine and cosine quadrature is what I mean. So the carrier is on cosine, the pure carrier is cosine, and the sidebands are put on a sine type carrier. So this is a block diagram of that, just showing you that sine multiplies times the small message, the narrowband message, where phi is much less than 1 in magnitude, and then you add the carrier term on. So that's called narrowband FM. And narrowband FM, we're going to come back and look at this after we do the analysis of the full spectrum of sinusoidal FM, as it's called. Narrowband FM is used for, in the lab when you're receiving the weather station, that's narrowband FM. Originally, police and fire and ambulances used narrowband FM. We'll see when we analyze the spectrum that the spectrum of narrowband FM is basically like that of amplitude modulation. And it's really no surprise because it's just that we're using a sine carrier and a cosine carrier, but there's no other terms in that. It's just that it's done with FM, and the fact that it's done with FM is also telling you that it's maintaining that constant envelope behavior approximately too. And you can demodulate it taking your choice of techniques, usually with something called the discriminator that we'll be talking about. So we'll come back and talk more about narrowband FM. It's part of the legacy of modulation schemes. So now what we want to do, this example just takes a sinusoidal case for the message and just brings it on through And when you take and find the expansion of it, you find that you get a pure carrier term, and then you get a sign at plus and minus whatever the message frequency is, where the amplitude is controlled by the deviation constant of the modulator and the frequency of the message. So I just drew a picture of the spectrum, and I pointed the sidebands up and down as if to say that they're shifted in phase, actually, because they're on sine carriers, and one has a positive angle and the other has a negative angle. Just comes about from the trig identity for sine times sine has that plus and minus. So it's just emphasizing that. But if it was the amplitude spectrum, the narrowband FM amplitude spectrum on the spectrum analyzer doesn't really look any different than AM does. You would see a central carrier that's strong, and you'd see two sidebands very weak, and you'd see nothing else, and you wouldn't really be able to tell the difference, because unless you're paying attention to the phase, which the spectrum analyzer doesn't do.
So how were you able to make the approximation that the sign of message, I guess one page back?
Right, just simply said the magnitude of phi has to be much less than 1. That's
Oh, no, I'm sorry. It was in the example.
Example 3.11.
Yeah.
okay.
There's an approximation on that second.
Okay. The approximation, oh, I see that there's a typo in here. There's a plus sign missing in here. So it should say omega CT plus FD over FM sine omega MT. Thanks for pointing that out. I'll change that and repost it since I've fixed a few other things recently.
And
then I'm saying that FD over FM is much less than 1 in this case.
Okay.
And then if I went through the standard trig expansion of that, I would end up in the trig expansion with, in the trig expansion, if this is true, if you have the cosine of where an argument is much less than 1, that's approximately 1, right?
Yeah.
And if you have an argument where you have a sine is much less than 1,
0.
well, it's 0 or the argument itself, right?
Okay.
For the small angle approximation.
Small,
And that's what you'd be doing here.
Okay.
Or you could just go through the power series expansion approach, and that would get you there too. Right now in the stepping stones, this seems kind of like, why are we looking at this when we haven't really gotten started? And maybe the order is a little bit awkward, but we'll come back to narrowband FM in a second. There's a variety of reasons why you might consider it, but I'm not so sure it's as significant. They're all as significant as they once were, many, many years ago. Okay, now we want to tackle is one of the more intricate things of this section. Still not like doing a convolution, though. It's a whole lot easier than convolving two functions. It's going after a special case of angle modulation where phi is beta sine omega mt. And I think phi could come from a phase modulation itself, or it can come from a frequency modulation, because if you integrate sine, you get a cosine, or vice versa. So this development will apply for whether it's FM or PM. There's just going to be a different constant that pops out, and we'll see that. You get a chance to study this more in the lab too when you play with looking at the spectrum of an angle modulated or sinusoidal FM modulated signal. So how do we're interested in the spectrum, because the spectrum of an angle modulated signal is actually kind of complicated. You can't get a simple closed form answer except in a few rare instances. You can simulate it very easily on the computer, and then you can use a tool like that simple SA function that I gave you and just do what's called a spectral estimate. But this particular form, when it's a single sinusoid or multiple sinusoids, you can do it exactly. So for the single sinusoid case, the idea is to go back to the complex domain again. So write the cosine of this guy here that has that angle phase deviation in it, beta sine omega mt, where beta is known as the modulation index. And it's like the A from AM. It's another parameter that you get to vary, but it doesn't have an upper limit of 1 like it does in AM modulation. But it's a parameter that controls the modulation in depth. Write that as the real part of a complex sinusoid. This is just the carrier, so just sort of ignore that for the time being, but study that term and say, what's going on here? Well, we've got an e to the j, but then we've got a sinusoid in the argument of that. And at first you can say, you can kind of hold your head and say, that's getting me all whacked out because I know e to the j theta from Euler's identity is cosine plus j sine of theta. But now you put a sine in the exponent. What is that? I mean, so you're right in thinking that's not anything like you've ever seen before, because I'm sure you've never had to deal with this before. But what you do know is true is that the sine is periodic, right? Sine omega mt is going to be a periodic wave. So we're now putting that in as the argument of an e to the j. So that also has to contain that same period, because that thing spins as it goes up and down with the periods of the sine in its argument. So it has a period that's just like the period of the sine sitting inside of there, but it's running through that complex exponential. So because of the fact that it's periodic, you can step back and say, Fourier series, what about that? It must exist. It's a periodic signal. There must be a Fourier series for that. It's like nothing else you've had to deal with before, but it must exist because Fourier series exists for periodic signals. So you go and plug this into the Fourier coefficient formula, and you get this integral that has the sinusoid in the complex exponential, and can be combined with the expansion function n omega m from the Fourier coefficient formula. And then you stop and you say, I don't know what to do with that. I never saw that integral before. But if you were to enter it into Wolfram alpha or some other tool, it would pop back an answer. Or if maybe you studied Bessel's differential equation in your differential equations class. Does anybody remember that? Well, so that's where the answer comes from. It's a Bessel function, and that he's the mathematician, and there's a whole bunch of different Bessel functions that are out there that are named after him, who made some discoveries involving solving differential equations. You don't see a differential equation here. You can think I have an integral equation here in the sense that I'm taking an integral. But this is a special function. So if you normalize it, like I'm talking about in this bullet, you actually get it into a form where you'd find this in a table, a math handbook of sorts. So you're integrating over one period, but now it's been converted to a period from minus to plus pi. And the bottom line is, for this class, is just to know that it's this Bessel function, and it's done. Okay, hit the wrong hotkey. What I was going to do was use a highlighter, but I'll just stick with the colors I'm using here. So this is, in particular, Bessel function of the first kind of order n with argument beta. So those are all important. It's in MATLAB, it's called Bessel J, for if you're interested.
Is that in relation to the Bessel filter?
Yes, it's the same guy. I think that involves Bessel's differential equation. I'm not positive. I mean, there's a differential equation associated with the polynomial that creates that linear system. Bessel functions have what are called recurrence relationships that allow you to derive one Bessel function from two others. And a recurrence relation just means that you can bootstrap yourself along to get higher order Bessel functions. Nowadays, because you're spoiled by computers, you're saying, why would I care about a recurrence? But in the olden days, when computers weren't that available, you'd have a handbook, and it would have two of the Bessel functions listed in intimate detail for a whole range of parameters, beta. And then if you wanted to get the next Bessel function order up from that, order n, suppose you had J0 and J1, you could get J2 from this recurrence, and then you could bootstrap yourself along. It's hard to imagine because you're so used to just clicking a button on the computer, but somebody has to still write those functions that solve that out on the computer, and they've still programmed recurrence relations into software. I mean, that's how they're solved. You just don't see it anymore. Someday you may crash into it when you're doing something and you have something crash, and then you have to go look and see how was this function written, and you may end up getting a little involved with it. I've bumped into it several times where you gotta do recurrence things. I was working on something with antennas that had a cylindrical waveguide feed, and that involved Bessel functions, and I had to write code for it that could take advantage of this recurrence relationship. Question?
What's the difference between recurrence and like recursiveness? Are you saying that you can on a higher order or
From a lower order.
Wow.
But you could rearrange this recurrence to run backwards. It's kind of like a difference equation. It's just what the mathematicians call it for special functions. They call it a recurrence. I guess you could look it up in Wikipedia and see what they say. I'm guessing that it would be something along these lines. A lot of special functions in math and physics that engineers also use have recurrence relationships. So those are the ones that are holding here. These symmetry properties, though, are important in our modeling of the spectrum that we're going to be looking at here in a second. So we will take advantage of those two symmetry properties. So here's what the Bessel functions look like when plotted. J0 starts at 1, so that's something worthy of remembering, and every other Bessel function starts at 0. That's just a property of them. And in the textbook, and I put it into the notes here, here's some of the zeros of the Bessel functions. In other words, where it crosses through 0. So J0, for example, crosses through 0 its first time, right here. And then it crosses through 0 again out here. And J1 crosses through 0 its first time right here, 3.83. These are some of the things you're going to notice when you're in the lab playing with frequency modulation and looking on the spectrum analyzer. Just verify that this behavior is true, and it kind of defines the shape of the spectrum too. We're not seeing the shape of the spectrum by looking at the Bessel functions directly, so we have to do a little bit more math to see how that comes into play. So now that we've got the Bessel functions to get the Fourier coefficients, that's what we were just saying, these are like the xn's are the jn betas, and then they're multiplied by e to the jn omega mt. That's the the expansion function in the complex Fourier series. All that's inside of this real operator now, and if you put it back together, you're going to get, because of the symmetry of the Bessel functions, jn and j minus n and so on, when you put this back together again, into real form, you get a cosine series. So you get the fundamental is at when n is equal to 0, and that's just the pure carrier component that you see right here. And then at n is equal to +1 or -1, you get this pair of sidebands. And notice they're spaced plus and minus FM, the modulating tone frequency about the carrier. And then the second harmonics involve J2 of beta, and so on. So it just starts, and then it goes out and out and out as a function of beta. So as beta gets bigger, the Bessel functions move off from 0. Remember, all the Bessel functions except for J0 start at 0. So when beta is 0, there's no sidebands. There's no modulation. And you just have a pure carrier. And I think that makes sense. As you drive beta up, you start bringing up all the Bessel functions above J0, and then the spectral lines start to pop up. So we should probably take the quiz. I'll just give you a quick animation, though, that I put together in Mathematica, which was running, so I didn't need to start it a second time. Here's a little animation now just to show you what happens as I increase beta. Sideband, I increase beta, and notice how the sidebands are growing. And we'll revisit this again later, but as I increase beta, more and more sidebands. And what does that mean? The spectrum occupied by just that single sinusoid is spreading out bigger and bigger and bigger. I call that the suspension bridge spectrum, because that's what that looks like, the cross-section of a bridge. You'll be observing that when you do the lab experiment on that stuff.